So, but the problem is this has 24 electrons, but I only have 22 electrons. It doesn't match. And so what I have to do is I have to correct this structure so that I end up with 22 rather than 24 electrons. Okay, now I have 22 electrons, but you'll notice the top oxygen does not have. There's count 2, 4, 6. This oxygen has an octet 2, 4, 6, 8. How about the sulfur? The sulfur has 2, 4, 6. And so we're lacking octets there. And if we're lacking octets there, then what we could try to do is, let's discount the electrons.
You do a double bond?
I only have 22. So what I have to try to do is maybe do some double bonds and see if that works. And let's see if I can get that to work. And so here, if I make this a double bond, then that will satisfy the octet on sulfur. Good. But I have a problem with this oxygen. This oxygen still doesn't have an octet. And so let me recount the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. 22 electrons. And so this is going to give us some trouble here. So what can we do? What did you do?
Double bond on the top oxygen.
Double bond on the top oxygen? And which electrons did you use to make a double bond on the top oxygen? These electrons here?
Yeah.
No. So you end up with this.
No, only a double bond on that.
Only a double bond on this one?
Yeah.
No double bond here? So you did this. Something like this?
Yeah.
Did it look like this structure?
That's what I got.
That's what you got as well? All right, let's count this, the electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24.
I think it should be 24 total.
Oh, yeah. I miscounted the electrons here. 6 and 18 is not 22. 6 and 18 is 24. And so, and so this one was okay. This has 24 electrons. So what we have to do is we have to make sure that these match. If they don't match, then it's incorrect. And so what we'll do is let me just start over here with this. It's going to be sulfur with 3 oxygens. And this is going to give us 24 electrons. So this is okay. 24 electrons matches with 24 electrons. What I did with the extra electrons is I completed the octets to the oxygen, which is what we want to do. But that leaves sulfur without an octet. And so in this case, we could form a double bond. If you pick the top oxygen, you get this structure. So we take a lone pair from here, drop it into the bond, we end up with this. But there are actually three choices of oxygen. I could do the top oxygen, I could do the bottom left oxygen, or I could do the bottom right oxygen. And so why did you pick the top oxygen? Was there a special reason you picked it? Symmetrical. It's symmetrical, but if you tilt like this, you know, and put the double bond there, it'd be symmetrical as well.
I don't think it matters because there's no top and bottom.
Yeah, it doesn't really matter, but there is a choice. There are three choices that we can do for the double bond. And so let's take a look at those three choices here. If I did the bottom left, I end up with this structure here. Like that. Do you know what these two are called? These two are called resonance forms. And we indicate their resonance forms by drawing a double-headed arrow like this. The double-headed arrow is reserved for resonance forms. And so the double bond could have been up here, or it could have been down here, or there's one more position for the double bond. What would that be? Yeah. And so we can have the double bond over here. Depending on which one we want. This would be it. And so we have a total of 3 resonance forms for this. One thing that's not good about this structure is what? There's one thing that's not so great about this structure. Do you know what it is? I'm sorry, the oxygens want 2 bonds, but sometimes it can't be helped.
Is it the formal charge?
It's the formal charges. That's not so great in these structures. What's the formal charge on oxygen here?
-1.
-1. And the formal charge here? -1. And the sulfur?
+2.
+2. +2 is fairly high. And then this oxygen? Neutral. And so the sulfur doesn't change. Here, it stays at +2. However, which oxygens are minus will change. Here. Octet is good, but formal charges are a little bit high. Is there a way to reduce the formal charge? There is. Let me do this as a side topic here. We're talking about expanded octets. In the 3rd shell and higher, the thinking goes like this. 3rd shell and higher has the potential to expand the octet. The reason is, let's look at the 3rd shell. The 3rd shell consists of the 3s and the 3p. This would be the 3rd shell. And what's the maximum capacity of electrons in the 3rd shell? 8 electrons. So if we fill up the third shell with 8 electrons, that's a, what shell is sulfur in? Third shell. And how many electrons does sulfur have? It has in its octet. It has 2, 4, 6, 8 electrons in that shell. And so it's filled. Could we fit any more electrons into the third shell? No, it doesn't fit. If we wanted to put more electrons, it would have to go in the fourth shell. And when we look at the fourth shell begins with what orbital? The 4s, and then the 3d. The 4s, as we call, are very big orbitals. The 3d are lots smaller. And so what's thought of, if there's extra electrons, that is, you can have more than an octet. So for example, if I had some extra electrons, we aren't going to put them in the 4s, but we can put them in the 3d because they're all the same N. And so extra electrons might go here. Okay, the disadvantage of that is it's going to cost you energy because you're putting electrons into a higher energy orbital. The advantage of that is you create more bonds. The more bonds you create, the more stable things become. So what's thought is this. And so this is probably what you saw. Right? You looked on the internet probably and saw this. I saw a lot of people draw this structure. So if you check online, what does the structure of sulfur trioxide look like? The structure of sulfur trioxide looks like this. Do you see that?
Saw that one actually.
You saw that one?
Yeah.
No. That's interesting.
It was like a generator.
What's that?
It was a generator, like a generator with a structure.
Oh, you mean an online Lewis structure generator?
Yeah.
Oh, that's pretty cool. Too bad you can't use that for the test. So that would be good.
Find it on the.
So we'll take a look at sulfur trioxide here. This structure is no good. You know why? This Lewis structure is not good. There's something clearly wrong with this Lewis structure here. What is it? There's no lone pairs on the oxygen. This only has 2, 4, 6, 8, 10, 12 electrons. This was at 24 electrons. So I'm missing a lot of electrons. If you go into organic chemistry, they often leave off the lone pairs. The reason they leave off the lone pairs is because they know they're there, but it takes time to write it. So just trying to save time. Everybody knows how many lone pairs on the oxygen, but do you necessarily? No. So you have to write it down. This structure is good. This structure has all the lone pairs. When you look at this structure, what are the formal charges in this structure? Yeah, they're all 0. And so this structure is good because all the formal charges are 0, except how many electrons now around sulfur? Oxygen remains in an octet, but sulfur has 2, 4, 6, 8, 10, 12. 12 pairs of electrons around it. And so here we're going to have 2, 4, 6, 8, and then what we have to do is we have to expand. We say expand the octet. That's 8, 10, 12, two more pairs of electrons form the bond. This violates Hund's rule, but we're creating bonds, so that's why they're paired up like this. It doesn't really violate Hund's rule.
So if we put it non-intergalactic rule.
Well, this, expanded octets like this is very common. 3 double bonds, this is very tricky because of the shapes of the orbitals and stuff. I'd hesitate before putting 3 double bonds there. But it turns out that, as you'll see in I'll give you a little preview. Let me bring this up. Give you a little preview here. This is from the Chem 1A book. Here are some unresolved issues we have encountered. Employing expanded valence shells. This is an expanded valence shell here, or expanded octet. Expanded valence shells and Lewis structures created the quandary of where to accommodate the extra valence electrons in such molecules as SF4, SF6. Specifically, are d orbitals used in the bonding description? So here we're using d orbitals to put the extra electrons. A related issue is whether to use expanded valence shells to minimize formal charges. So we use the expanded valence shell to minimize the formal charge in this particular case because the formal charges were a bit high here. And we could bring them to 0 by expanding the valence shell or expanding the octet. Formal charges in anions such as sulfate. Still, another issue is whether Vesper, we've been talking about Vesper today, for hybridization schemes, the valence bond method gives more fundamental view of molecular shapes. Finally, we might wonder, how the valence bond and molecular orbital. Actually, we're not even going to talk about this theory. Really more Chem. So, long story short, is they've done some theoretical calculations to calculate how much D participates in the bonding for a molecule like this, and there's like no D. And so, the current thinking is like this, and our Chem 4 book hasn't caught up to current thinking. The current thinking is if it's always going to maintain an octet. So sulfur here is not going to go more than an octet. An octet is 2, 4, 6, 8. But the more bonds we form, the better. Now, I think you asked this yesterday, Colin, about the charge and the ionic bonding that could occur due to the charge. I mean, this whole thing is neutral. But there is going to be an ionic bonding component to this. Not necessarily here. There's going to be some ionic. There's both covalent bonding here and ionic bonding because of the charge. This is +2, that's -1, so the opposite charges attract. And so we have both covalent and ionic. If we have something like SF6 is impossible to bond 6 fluorines to this without expanding the octet. But there's another way of doing it, and the other way of doing it is just to maintain an octet here. So that would be SF4, and then the 2 extra fluorides would be ionically bonded to it. And so this fluoride would be ionically bonded to these. These are called resonance structures here, but these are different kind of resonance structures. Rather than moving around the double bond here, like we did here, they're moving around the ions here. So this one flips from being a fluorine covalently bound to a fluoride being ionically bound. And this way we don't have to violate the octet rule. The octet rules is maintained. But this is an advanced topic. I don't want to talk about this. Actually, I'd rather just avoid talking about this right now. But so what does that mean for us? You know, where do the extra electrons go? You know, where do the extra electrons go on the sulfur atom? And so this is talking about this. Although, you know, all this is appealing. You know, expanded octets and expanded valence shells are appealing. It has come into question because quantum mechanical calculations have shown that the wave functions contain very little contribution from d orbitals. Now, here we would expect significant contributions from d orbitals because that's where the electrons got to go. Electrons have to go in the d orbital. So when you look at the quantum mechanics of it, it doesn't seem to be correct. And so at the end of this section here, they say, well, probably the best for right now is to just, okay, that was it, that was the end of that section. The best thing to do is just to go max up, just octet. Just keep it the octet. We're not going to expand the octet. And so you might see sulfur trioxide with 3 double bonds, but we're just going to keep it with an octet and high formal charges. And so which one do you write? You write these. Okay. That'll solve. We're not going to go past the octet. Okay. That's just, and we're going to just suffer with the high formal charges. Now, that poses a problem with something like this. Let's see if this is... That poses a problem with these structures here. Because if you look at sulfur, there are 2, 4, 6, 8, 10, 12 electrons. Like that. And so this would be an expanded octet. Well, what they're saying is no, it doesn't expand the octet because the theoretical calculations show that the d orbitals are not significant. And so for a structure like this, which they say, this is our chemical book, molecules with more than 4 electron pairs around the central atom. They say that up to now, we just dealt with octet. Atoms of elements in the 3rd period and higher, so that's the 3rd shell and higher, can have more than 4 electron pairs surrounding them. This is accomplished by involving d orbitals in the formation of covalent bonds. However, this is just a little bit behind because the d orbitals may not be participating. And so this is how I learned it. I learned it by d orbitals participating. But the calculations are getting more and more sophisticated because the computer is getting better and better. And so what we do for something like SF6 is like this. For SF6, we'll have 4 of the fluorines covalently bonded. Like this. So what does that make the formal charge, formal charge on sulfur? So we have +2 charge. And then the fluorines really want electrons. Fluorines are the most electronegative species. We form 2 fluoride ions, and then this would be a cation here. 2+ or +2. right like that. And so 4 of these fluorines are held together by covalent bonds. Two of them are held together by ionic bonds. So the ionic bond's not shown by a line, it's just shown by having the ions adjacent to one another. When we form ionic bonds, we try to form as many, if I have a cation, I want as many anions around it as possible. Well, how many anions can I fit around this? Well, I got all these 4 fluorines here. I can't fit any fluorides over here. And so I can only fit 2 fluorides here. For a structure like this, PF5, we max out at the octet. So 4 of these would be covalently bonded, and the 5th one should be ionically bound. And so that's what you deal with in Chem 1A. But we're not there yet, so I don't want to teach the expanded octet if you're just going to revert back to just having an octet. All right, so we end up with 3 resonance forms here. Resonance forms are important to draw out. What happens is that a lot of people think that the double bond just jumps, like from position to position, and so it's resonating, rotating like a propeller or something like that. But that's not really the case. This is a drawback of what we're doing with Lewis structures. What's actually happening with the electron cloud density here is something like this. This is showing us how the electrons can move in the structure. And so what people think is like this, interconverting between resonance forms. So let's start off with this resonance form here. And what I can do is I can take this lone pair and make a double bond here. If I do that, then there's too many electrons around sulfur. I don't want to exceed an octet. And so if I end up with too many electrons around sulfur, I got to kick some out. And so let's kick some out onto this oxygen here. And this is going to generate our first resonance form here. I mean, this is our first. This will generate our second resonance form here. The third resonance form we can form just by taking this lone pair, making a double bond here, and then kicking this pair out here, making that a single bond. So we end up with this. So what we say here is that the double bonding electrons, this double bonding electrons is spread out through the 3 sulfur-oxygen bonds. And so what we have is, if we have a double bond, we have twice as many electrons there. And so one way of thinking about this is like this. And the electron cloud can move in the structure. So let's say you have a bathtub that's shaped like this. And let's say you try to put 2 feet of water here, and 1 foot of water here, and 1 foot of water here. Would that work? No, if you try to put 2 feet of water up here, what's going to happen? It's just going to spread out over the entire structure. Unless we block it off. If we walled this off, then it would work. And so we have something called localized and delocalized. So for example, here I could put 2 feet of water here if there's no way that could get over here. That's called localized. But in this case, when I draw resonance forms here, it's delocalized because there is a way the electron cloud can spread out. And so neither of these structures is really correct. But that's the problem with Lewis structures. Lewis structures, are we doing any Schrodinger equation type stuff, quantum mechanics, calculations? No. This is just by hand. You know, we aren't dealing with all the physics of this, and we don't want to deal with all the physics. We just like to do this by hand. And so what we have to do is we have to do this. We end up making something called a hybrid structure. So if you try to do this, what's going to happen is you're going to end up with the resonance hybrid. And can you tell me how much water is going to be in each leg of the tub?
1.3.
Yeah, 1 1/3, right? And so it's going to be 1 1/3, 1 1/3, 1 1/3. It's just going to spread out evenly. So when they measure the bonds in sulfur trioxide, all the bonds are exactly the same. All the bonds are exactly the same, then it's not resonating. That is, 1/3 of the time it's double, 2/3 of the time it's single, the top. This bottom left, 1/3 it's double, 2/3 it's single. It's not resonating like that. Instead, what's happening is we just have it stable. It's 1 1/3 bond. Well, how do you show 1 1/3 bond? The usual way we show 1 1/3 bond is by doing something like this. The oxygens here. And so we just spread out. These are called the double bonding electrons, or the pi bonding electrons. Sometimes you'll hear that. And it's just spread out over the whole structure. And this makes all the bonds equal.
How would you show if it's 1 1/2 or 1 1/4?
How would you show? You don't show it. You just, in this case, you know, it's going to be spread out over 3, and so it would be 1 1/3. But you'd have to state it. If you just see this, you can't tell the difference between a 1 1/2 and a 1 1/3 and a 1 2/3. You can't tell the difference. And so the only way you can tell is by looking at the whole structure. The formal charge does the same thing. The formal charge is not if I look at the formal charge, it's negative 2/3 of the time and 0 1/3 of the time for all the oxygens. And so what we end up doing with the formal charge is we have a -2 charge spread out over 3 oxygens. And so the formal charge is negative 2/3 on each of these. And the bonds are 1 1/3 bonds. That means there are 2 lone pairs that are fixed on each oxygen, like this, and 1 lone pair that is delocalized over the 3 oxygens to give us a negative 2/3 charge. And so a total of -2 distributed over 3 oxygens. The sulfur remains at +2 throughout, including in the hybrid structure. Will be +2. In organic chemistry, the more resonance forms you can draw, the more stable. Because the more you can spread out the charged electron cloud, the more stable. The more concentrated the electron cloud, electron charge is, the less stable things are. And so do the resonance forms here. So if we look at this one, nitrogen dioxide, nitrogen dioxide is weird. Did you guys have that?
No,
Okay,
it's sulfur dioxide.
you had sulfur dioxide. Let's take a look at nitrogen dioxide. When you do nitrogen dioxide, nitrogen is 5 electrons, oxygen is 6. So that's 2 times 6 electrons. There's 0 charge. And so that gives us 17 electrons. If we have 17 electrons, it's an odd number of electrons. When we draw out the Lewis structure, the best Lewis structure we're going to come out with looks like that, where we're going to have 1 single electron on that nitrogen. This oxygen will have an octet, and this oxygen will have an octet. But does the nitrogen have an octet? No. So what did I call this single electron before? Do you know what I called that?
Dangling.
A dangling bond. There's another name for it. Do you know the other name for it? It's called a free radical. Free radicals have dangling bonds. And so what a free radical wants is it wants to take an electron to complete its octet or bond with something and share an extra electron to complete its octet. So it's either going to form a bond or take an electron. And so free radicals are going to try to react with something by oxidizing them. How many resonance forms can you draw for this? 2. Yeah, we could have formed the double bond over here, which we did, or we could form the double bond on the other side. And so this one only has 2 resonance forms. So the other resonance form for this would have had the double bond formed from the right oxygen and the single bond on the left oxygen like this. That would have been it. In reality, I can't put 2 feet on one side and 1 foot on the other. What am I going to have?
1.5 in each.
Yeah, 1.5 each. And so the hybrid, this is called the resonance hybrid. Is going to have 1.5 feet on both sides. And it's not going to be 0 and negative and 0. It's going to be, well, you have a negative charge distributed over 2 oxygens, so it's going to be -1 divided by 2 oxygens. Here's the -1/2. So there are 2 lone pairs fixed and 1 lone pair that is delocalized here. And so we have a -1/2 here and a -1/2 here. This is electron cloud density, and this is going to be 1.5 bond. And both of these are 1.5 bonds. We draw them exactly the same as that, The only reason you know it's 1.5 is because it's just delocalized over 2 bonds rather than 3 bonds.
So are we going to be confronted with these like relatively often?
No. You're going to have to know how to draw resonance structures. And so let's get some practice with this. I'm going to give you some Lewis structures to draw out right now. Okay, I want you to draw the Lewis structures for CO3 2-, HCO3-, and H2CO3. H2CO3 is unstable, right? H2CO3 decomposes, but just draw the Lewis structure for H2CO3 because you can draw a stable structure for this. If there's resonance forms, can you draw out all the resonance forms? What are these?
Did you do the resonance hybrid as well?
The resonance hybrid? Yeah, if you're feeling ambitious, do the resonance hybrid.
You feel
Yeah. Yeah. Well, it has an octet, doesn't it? So it doesn't violate the octet rule. Why can't I put it with a double bond? Is that a rule or a law? Well, I shouldn't. I shouldn't because why?
There's two options that would take it.
I'm sorry?
The other two options are more likely to take it.
Yeah, that's true.
It's like a downhill, it's like a down street.
Yeah. But do you see something different about this structure versus the other two? What else is different about this structure versus the other two?
There's no charge.
Although, carbonate, you're right, we pick each of those and draw out the 3 resonance forms for carbonate. But bicarbonate, there's a problem with this one, and the problem is
The formal charge.
the formal charges, right? What are the formal charges here? The formal charge on this oxygen is this one, plus. So you have 3 oxygens, but one of them is going to be the loser to this. So if these 2 oxygens got into tug of war, who's going to win necessarily? Or maybe, well, it looks like this oxygen won. This oxygen lost. Because up here we only had 1 oxygen with a formal charge. Here we have this. So what we did was we took an electron essentially off this oxygen and effectively gave it to this oxygen here. Does that seem very stable to you? If you have a tug of war between 2 oxygens, they should be pretty comparable in terms of strength. Their electronegativity is the same, 3.5. And so this structure is not stable. Does that make sense? And so we're going to eliminate this structure. If we eliminate this structure, then how many resonance forms do we have? 2. But then you might go, well, can't we move the hydrogen? Can we move the hydrogen around? In resonance forms, we never move the atoms. We only move the electrons. And so do not touch the atoms. And so normally on a test, I'll see a whole bunch of resonance forms where they keep moving the hydrogens around. Not only that, some people will flip this. So they'll tilt this like vertically, and then they'll have this, it'll look like a Y. And so they'll have this as the resonance form. Is that a resonance form for this? Well, some people will say, yeah, that's a resonance form, But no, it's not. And so what we have to do with resonance forms is you have to make sure the atoms never move. The only thing you're going to move are the electrons. And so resonance forms are just looking at different ways of distributing the electrons.
So how would you draw the hybrid?
How would you draw the hybrid? Okay, let's take a look at the hybrid. So this would be carbonate here.
I know, that's why it's a
So the hybrid would be based on the first 2 structures here. And so the double bond can either be here or here. And so what we're going to do is we're going to delocalize the double bonding electrons over both bonds. And so this would be like 2 feet and 1 feet. But really, if it's like water or like fog, it's just going to spread out evenly. And so what we're going to end up with is a 1.5 bond, 1.5 feet. And then we look at the formal charge. The formal charge switches between these 2 oxygens here. Again, we're eliminating this structure here. And so what is the formal charge on each oxygen here? It's a -1 charge distributed over 2 oxygens, so it's going to be -1/2. This will be a -1/2. This will be a -1/2 here. And then this just stays as is. This is not going to be impacted here. And so the sum of the formal charges, -1/2 plus -1/2, gives us a net charge of -1. And so this will be the hybrid structure. Okay. There are different ways that people write hybrid structures. how they do the dots and that kind of stuff. And so let's take a look. HCO3 minus hybrid. Now here they wrote dashes, but this is a ball and stick model. This is bad. Why? It doesn't matter if it's kinked. Actually, it is kinked. The COH. Do you see it's kinked like that?
No lone pairs on
There are no lone pairs on the oxygen. What do they do with negative charge? They just put the negative charge out in the middle here. Now, it's negative 1/2, so they just put a negative charge there.
Is that how you would see it in OChem though?
In the OChem book, let's take a look at how you'd see it. A bicarbonate is not that common, as common in OChem. What's more common is acetate. Let me show you what acetate looks like. I don't see it here. This is typically how you see it, but they usually write a curve. Let's see if I can find it. Okay. Let me draw it. The way you would typically see something like that in organic chemistry is they draw it like this. You just have a dashed line throughout the whole thing. I mean, it's not that big of a difference, but that's it. And then they wouldn't have the formal credit there. I'm surprised I can't find the image of that. Like this. And usually they'll draw a curve rather than things like that. How about H2CO3? How many resonance forms did you get for that?
Is it just
It's
one?
just one.
Yeah. There's only one structure. So there's no resonance form for this. It's going to look like this. This would look like.
That would mean there's no resonance hybrid, which is the,
Right.
or would you say it is the resonance hybrid?
No. There's no resonance hybrid. You have to have more than one structure to do that. And so it's only one structure. If there's only one structure, there's no resonance form. there's only one place where we're going to draw the double bond. We could draw the double bond here and here, but the formal charge would be too high. And it wouldn't be a stable structure. All right, let's take a break and then we'll start up after the break. Uh-huh. So we have a couple of exceptions to those structures here. One was when we have more than 4 things bonded to it, like 5 or 6 things bonded. Another is with fluorine. Like we could easily make an octet with beryllium here by just double bonding. And so if I have beryllium difluoride and I just do this, then everybody has an octet. And so the octets are satisfying. But the problem is with the formal charge. The formal charge on fluorine is what? Not negative, but positive one. So fluorine is positive. This fluorine is positive, which means beryllium is what? Beryllium should have 2. It has 4. So beryllium is going to be -2. Now think if there's a tug of war between beryllium, which is on the far left, and fluorine, which is on the far right, who's going to win? Fluorine. And so this means that beryllium overpowered 2 fluorines to take 2 electrons, 1 from each. And so this is never going to happen. Fluorine will never form a double bond because in order for fluorine to form a double bond, it has to give up 1 electron and share it. And so fluorine never double bonds.
That's because fluorine will always win the electron.
And fluorine will always win the electron. Fluorine's the most powerful oxidizer on the chart. It would be very unusual for fluorine to lose an electron. In fact, it doesn't. Not with the compounds that we deal with. And so we're stuck here. We're not going to get an octet around beryllium. But that's okay. Beryllium's not very electronegative. The same thing happens with boron. We'd like to form 1 double bond here, and then we can get an octet around boron, but it's not going to come from fluorine. Now, if there's an oxygen bonded to this, yeah, sure. Then we could double bond it. Boron can be an octet. And so here, these are Lewis structures with less than an octet. So one of the things that I was talking about was the quantum mechanical calculations. The quantum mechanical calculations are the full theoretical approach to these structures. But we aren't doing that. We're just doing paper and pencil. When you do paper and pencil, you know, this is the best structure for O2 that we have. 0 formal charges, everybody has an octet. But this structure is not accurate. This structure is not accurate because O2 has unpaired electrons. When there are unpaired electrons, we call it paramagnetic. You don't need to know that yet. But if it has unpaired electrons, it's attracted to magnets. Have you ever seen a stream of water being attracted to a magnet? Yes? No? Let's take a look. If we have a good video. This is one 1 minute, 50 seconds. 1 minute, 16 seconds. We'll try this one.
Good motion.
So they just put a charge on that. This would be more electric. Water has positive and negative ends, so it can be attracted to, let's say, a negative or positive charge build up on the cone.
So it's not because of the ions.
No, there are no ions. Let's see, did they do a magnet? Oh, that was false electricity. I think, let's see. Let's do a magnet here.
I'm confused that can be attracted to more positive and negative.
Yeah, we're going to talk about that in the next chapter.
Is that the only substance that
No, there are other substances that do this. That's what, I don't know if the volume is going on the volume here. All right.
Why has nobody got magnets?
Okay, so they build up some static electricity. Okay, that is water, but what about oxygen? Let's take a look at liquid oxygen. And a magnet. Let's follow that now.
Exposed to a magnetic field. This effect is known as diamagnetism. That's just a fancy way of saying that each of the nitrogen molecules is repelled by the magnet's magnetic field. So, when a coil of liquid nitrogen passes the magnet's pole, it doesn't look like anything special happens.
Yeah, nitrogen is not magnetic. It's what we call diamagnetic, so it just passes through the magnet as if there was nothing there.
The nitrogen just falls past the magnet. That's because the diamagnetic effect is very weak, so we don't normally observe it. All materials are at least slightly diamagnetic, but because the effect is so tiny, we don't normally notice it.
Just like nitrogen, oxygen isn't normally magnetic. And just like nitrogen, each molecule of oxygen behaves like a tiny magnet when it's exposed to a magnet's magnetic field. Oxygen behaves differently than nitrogen does. The way oxygen behaves is called paramagnetism. That's a fancy way of saying that each molecule of oxygen is attracted to a magnet's magnetic field. So, when I pour the liquid oxygen between the poles of the magnet, it sticks. And we can even make a little bridge out of liquid oxygen that will stay there until the oxygen finally boils away.
Liquid oxygen is very dangerous stuff. You don't want to contact any organic materials, things that are easy to burn, because you get explosions. So you always watch out for liquid oxygen. But the reasoning goes like this. If you draw the Lewis structure like this, all the electrons are paired, 2 lone pairs, 2 bonding pairs, 2 lone pairs over here. But in order to be attracted to a magnet, there has to be unpaired electrons, like a free radical way. And so they chose to draw this, but neither of these are correct. Normally we'll just draw it like this and realize that that's not great. You know, what we really need is a full quantum mechanical approach to this, not just summing up the valence electrons and that kind of stuff. The full quantum mechanical approach is called molecular orbital theory. And let's talk about Chem 1A. In Chem 4, we don't talk about it. So I'm not going to talk. Here's some liquid oxygen here. And so just, you don't have to worry about this just yet. Just know that doing Lewis structures, we don't always get the right answer. When we come up with the resonance structures, it's not correct. So we have to come up with a hybrid. And the hybrid, well, you have to figure that out based on the resonance structures. Let's take a look at ionic compounds and other types of bonds. So the types of bonds that we dealt with so far: ionic, polar covalent, non-polar covalent. It depends on the delta En. Now, the delta En is big, we have ionic. If it's medium, we have polar covalent. If it's small, we have non-polar covalent. Okay, then there's one other type of bonding that we're going to discuss in this chapter, and that's going to be metallic bonds. Metallic bonds. One of the properties of metals is they have loosely held electrons. And so the way it's explained is this. This is the electron C model. The electron C model. The electron C model is nice because we don't need any math. We don't have to do any computer calculations. The best is the full quantum mechanical treatment of this metal, which we could do. And, it's pretty much molecular orbital theory, but expanded. We call it band theory. But for us, we'll just suffice with the electron C model. The electron C model has the nucleus and the core electrons. Nucleus and core electrons. Fixed. And so the nucleus is going to have some positive charge, and the core electrons won't balance all that positive charge. So we'll get a net positive charge. It would be net positive 1 or net positive 2, like in B. So plus 1 or plus 2 or whatever. And these are thought of as like the pier pilings, you know, on a pier. And then the pier pilings are in the ocean, and the ocean are the valence electrons. So these are the valence electrons, and this is the sea of valence electrons. And the sea of valence electrons, the valence electrons are free. They're free to move wherever they want to go. Yeah. And so this would be the electron C model for metal. And so this would be something like sodium metal. We have the core, we have the nucleus, and this would be the single valence electron. This would be like magnesium metal here, a little higher charge. We can have mixtures of metals. Do you know what mixtures of metals are called? Alloys. So we could have homogeneous mixtures. So we might take a sodium and in there. That seems a little bit bigger, so it might disrupt the structure a little bit. But we can vary the composition of the mixture. That is, we can vary the composition of the alloy. We call that a substitutional alloy. Sometimes you can fit, atoms in between, like here. There might be a little bit of space and you can fit a small atom in here. Sometimes they call those interstitial alloys, in between the spaces. But what we have here is we have delocalized electrons. And so the electrons are delocalized throughout versus localized electrons. Localized electrons will be fixed, like the core electrons that are fixed in the nucleus. Those don't move. Just the valence electrons here are delocalized. The same thing when we have double bonds here. The double bonding electrons are delocalized here. That is, they're spread out. Whereas these single bonds here are localized. Those aren't going to move. They're stuck where they are. Here are some common alloys. 18 karat gold is 75% gold, 12.5% silver, and 12.5% copper. I don't know how precise that is. Is it 75 plus or minus 1%, or is it right on 75? That's 75.0000%. There's lots of different compositions of brass. There's, 18 karat gold should be this. I'm sure it varies slightly on who makes it. Brass, many different formulations of brass, copper and zinc, anywhere from 60 to 95% copper and 5 to 40% zinc. Bronze is a copper tin alloy. Carbon steel is just iron with some carbon atoms. Sometimes there's silicon and some other elements, nickel, whatever. Stainless steel has nickel in it. Oh, here's stainless steel. Stainless steel has mostly iron, chromium, nickel. The chromium and nickel really help prevent corrosion of the iron. And so you have there are many different formulations of stainless steel. Pewter is a tin antimony. You don't need to know any of these. Sterling silver is silver and copper mixed. And so it's easy to make alloys. You just substitute atoms here, or you stick atoms in between atoms. Mixtures of properties vary. All right, there's one other type. We look at molecular compounds, right? Here. Molecular compounds. But we also have something called covalent network or network covalent compounds. And so CO2 is a gas. What do you think SiO2 is? Carbon and silicon are in the same family. Probably a gas. You would think SiO2 is a gas. But SiO2 is not a gas, it's a solid. And it has a common name. Do you know the common name for SiO2? The common name for SiO2 is quartz. So why are the molecules so different? CO2 versus SiO2. And the reason is because SO2 is what we call a molecular compound. But SiO2 is not. SiO2 is called a network covalent compound. And so it doesn't form molecules. What it forms is a lattice. And it's a lattice that's held together by covalent bonds rather than a lattice held together by ionic bonds. Each silicon in this lattice is bonded to 4 oxygens. If each silicon is bonded to 4 oxygens, shouldn't it be SiO4? Yeah, you would think it'd be SiO4. However, each oxygen is bonded to 2 silicons. And so we have to split this oxygen in half. Like half belongs to this, the other half belongs to that. And so if we split all these oxygens in half, then we end up with that, SiO2, even though there are 4 oxygens bonded to this. And what we form is we form a lattice structure like this that just extends out in 3 dimensions. Here. And so let me give you a better structure on quartz. And here's quartz crystal here. Or no, this is not quartz crystal, that's diamond. So let's take a look at quartz crystal. We'll take a look at the quartz lattice. The view of the quartz crystal. So this is all held together by covalent bonds. Here's a close-up view. Here's a view of the silicon bonded to 4 oxygens, but each oxygen is bonded to 2 silicons. So, that's what we end up with. And then we have ionic lattices, which we talked about earlier. We looked at an ionic lattice from earlier. All right, chapter 12 and chapter 13. Well, here's another example. This is network covalent lattice. Do you see that? This is network covalent lattice of carbon atoms. Each carbon atom is bonded to 4 other carbon atoms here, and it just extends. These are covalent bonds. This is diamond here. That would be the structure. Diamond is network covalent. This is graphite here. Graphite has a different structure. This is graphite, which has these layers of covalent. So this is like covalent lattice here, except this forms a sheet. And between these sheets, there are no bonds. So these sheets can slide on top of each other. And it gives it graphite different properties. Here's also, this is a giant molecule here. This is a molecule of C60. There's 60 carbon atoms. This is called the buckyball. And so it's a molecular compound with covalent bonds, non-polar covalent bonds. All right. What we're going to do is take a look at chapter 13 here, which is a continuation of chapter 12. What we're going to do in chapter 13 is we're going to try to do a 3-dimensional structure of these. In a Lewis structure, you just draw it flat, you know. But what we're going to try to do is try to do these 3-dimensionally. And the reason we need to do this is because it's really important for properties. In fact, let's take a look at a video here. I want to show you. It's an old video, but it's pretty good. But it talks about the importance of the structure, the 3-dimensional structure. So let's take a look at this. Not only that, we need to know, how the electron cloud is distributed in this. Especially things in terms of bond polarity, bond polar, more polar or less polar. So let's check out this. Can you hear that okay? Too loud?
production of the Chemical Education Material Study.